Okay, we are live, I think. Okay, let's wait a couple of seconds to let people get in the session, and then we can start. Okay.
I guess in the meantime, while other people join, you can, if you go to the feed tab, you'll see the link to the orchestra app that we'll be using for the workshop. So you can click on the link and you will be in the orchestra app, and you can see all the workshops. And the one that we will follow in this session is NewWave. So if you look in the table, you will see one workshop with the title that I just posted in the feed, and you can click on that and launch, and it should create an RStudio session in which you can log in with RStudio as a login and RStudio as a password. So those of you that are already in the session, you can start doing that because it will take some minutes to start, especially when we do it all together.
Okay, we can start. So welcome to this workshop. The speaker is Federico Agostinis from the University of Padova. And he's now presenting his BioC package, NewWave, an R package for dimension reduction and batch effect removal for single-cell RNA-seq data. So Federico, if you're ready.
Thank you. We developed these packages in order to have a good method that can work also with HDF5 files and the layered array. So the objective of this workshop is to learn how to use NewWave with different hardware, because the best way to use it can change in order to the number of cores that you dispose. I will give a really brief introduction about the model. NewWave assumes a negative binomial distribution for data, where the mean parameters is related to a single observation, while the dispersion parameters can be equal for all the observation or related to a single genes. The estimation of the mean parameter is done as you can see here, where there is X is the matrix of the batch, or in general is the matrix of the cell-related variables. You can put whatever variables you want related to the cell. V is the matrix with the genes-related variables, and gamma is parameters, while W and A are the reductor dimensional matrix and this weight matrix. The dispersion, this is the function of the dispersion parameters. There are three steps used for the estimation. There is the initialization of the parameters that is done using ridge regression for B and gamma, and with a PCA for W and alpha. After that, there is the optimization of the dispersion parameters. It can be parallelized only in the generalized option, and the optimization of the cell-related parameters that can be always parallelized, and the optimization of the genes-related parameters. We will see why it's important to divide these steps later. The initialization is done only once in the process, and the initialization. The optimization, these three steps of optimization are done iteratively until the convergence of the algorithm. In order to reduce the memory consumption of this method, we used a PSOC cluster that can work both with both in Windows and Unix system, and the R package shared objects that allow to share metrics between cores, and this avoid memory duplication. Thanks to this implementation, the estimation process can be parallelized, and it has a huge benefit in terms of time consumption. In order to reduce even more the time consumption, we studied some mini-batch approaches, and there is the mini-batch can be done at each step of optimization. So it can be done on the optimization of the dispersion, of the cell-related parameters, and the genes-related parameters. We will work on splatter-generated data. Splatter is an R package designed to generate the single-cell transcriptomic data with a good level of customization. We need a batch effect for this workshop, and we need also some group label that we can think like cell label, cell type, and we will use this cell type in order to test the result of low-dimensional representation using clusterization. You can see.
Okay, so sorry, Federico, to interrupt. So
yes.
Perhaps this is a good place to stop for a second and see if if you want to follow along the workshop. In my case, I started the RStudio session right when we started the workshop session, and now it's ready. So okay. Maybe I'll just do a quick poll. Are you able to run RStudio?
Yes, you can see my RStudio.
No. I mean, we can see your RStudio, but are people able to run their own RStudio on Orchestra? It seems that the majority can. If you can't, maybe send me a direct message on the platform, and I can help you out with the. I mean, if you can't and you don't want to, that's fine. But if you want to and you can't, send me a DM message, a direct message, and I will try to help you out. The other thing that I wanted to mention before we start the actual code, I think Federico is happy if you interrupt with questions. So you can either use the Q&A feature or maybe raise your hand, and we can add you on stage to ask your question on, by voice. And also, this could be a good moment to ask questions about the model if the model is not clear. Otherwise, Federico will.
Okay.
Okay. So if you have issues with the Orchestra app and you want help, just send me a direct message. Thanks.
Okay. Thank you. Yes, you can. Please, you can see that we will go to generate 1,000 cell. It's better if we reduce this to 500 because there is some issue with the parallelization on Orchestra. We will see that we will not have an improving in time consumption using more than one course, but I think that it is related to Orchestra because we don't have more than one course disposable for this workshop. So in the real case situation in your laptop, this will work, but now it will not work. So I will go to generate data. If someone has never generated some data with Splatter, it generates a single cell experiment with the counts with the data in counts slot, and this is the single cell experiment. We can see we have 500 cell and 10,000 genes, and the class of our counts is a matrix. For this workshop, we will use only the 1,000 most variable genes and the 500 most variable genes. And an important in the call data of this single cell experiment are stored some important variables. The most important one for us is the batch effect. You can see batch 1 or batch 2. And also there is also the group variables, that is our cell type. So a fundamental factor for using NewWave is that the batch variable in call data is a factor variable. As you can see, here is a character variable, so we will change it. And when you will use NewWave in your real case situation, please be aware that it is really important to have a factor. And we can see with the PCA and TSNE how our data are distributed. We can see that the shape of the point is related to the batch and the color is related to the cell type. There is a clear difference between the two batches, and the objective of this workshop is to correct it with NewWave while we reduce the dimensionality. It's important to solve a batch effect, because if we done a clusterization using k-means with the latent representation of the PCA, we can see that our adjusted random index is very low, is only 0.1. And if there are not questions, I will start to effectively use NewWave. Okay. Some basic advice. There is the verbose option that explain some information about the model. Is default is false, and I suggest it to keep false, especially with the very large computation. In this workshop, I will always set to true in order to help understand this model. And we have no concern about the dimension of the Minibatch, but I always use the 10% of the cell and the 10% of the genes. So I suggest you to use the same quantity. There is the standard usage assumes a common dispersion for all our genes. It uses one core, and it uses all the observation for the estimation process. The parameter k is the number of the dimension of the latent representation. The x parameters represent the x matrix that we have seen before, so the matrix of the cell-related parameters, cell-related variables. So when you will want to correct batch effect, if batch is the name of your variable in call data, this is the way to use it for the batch effect removal. I will run the code. As you can see, there is a setup that starts the cluster and creates the matrix. The initialization, that is the part where there is the ridge regression and the PCA, and then we can see the time of each one of the optimization, the dispersion optimization, right and left, and the time of each one of this optimization, and the result in terms of likelihood of each one of this optimization. There is also an orthogonalization of the matrix V and alpha. The iteration continues until a certain number of iteration is done, or a certain difference between the log likelihood is reached.
A question. There is a question, Federico. Yes. Any advice on choosing K?
No. You can choose the best K you want. I always use 10, but if I think is related to the number of genes. So 10 could be a good number to 500 genes or 1000 genes. If you start to use 10,000 genes, maybe it's better to increase the number of K. If you use only 2K, you will not have a good results. So try to relate it to the number of variables you start.
Yeah, so if I can add a little bit on that, it's obviously like a very hard problem to choose the right K. I think what for example, what Brita said in the keynote is very relevant here too. I mean, the problem is that we don't have. It's not like PCA where if you select a very large number of factors, then you're guaranteed that the first factors are the same. So here, for example, if you run with k equal 11, it's not that the first 10 are the same and then you have the new one. So it's not as straightforward as in PCA, for example, to select a very large number and then select down. We have, in principle, you can use some kind of usual sort of a model selection approach to select k, like AIC or BIC criteria. But in practice, usually you want to just choose one or a few values and then maybe look at some exploratory data analysis or some sensitivity analysis. I think values between 10 and 50 are usually what we use in practice, but there isn't really a good guidance as of now on how to best select k. I think this is kind of similar for all these like factor analysis models like GLM-PCA and MOFA and all the ones that have been developed so far. So this is, I think, it's a good area for the research on how to best select number of factors.
Thank you. This second model has been put to make you see the difference when there is an increase of number of cores that is set in children parameters. But as I said before, here in orchestra, I will not have an improvement in time consumption, so I will not run this command because I will have the same result of the command we have just seen. So I will go to the second part to make you see how use the mini-batch approaches. As I said, there are a mini-batch for all of our optimization step. So when in this case we are using a common dispersion, the common dispersion optimization with all the mini batches is the best way you can use NewWave when you don't have a large number of cores. This is because the generalized dispersion is slower, but it can be parallelized. So if you have a lot of cores, you can use generalized dispersion and parallelize. If you don't have a lot of cores, I suggest you to use the common dispersion and the mini batch. So using the parameter nGenDisp, you can set the number of genes you will use in this optimization. We have 500 genes, so I suggest you to use 50 genes. And the same is for nGenPar. It means is the parameters to use to set the number of genes that you will use in the genes related estimation. And I will set it to 50, and the same for NSLPar. So we have 3 different optimization and 3 parameters for the optimization for the mini batch of this optimization. The first iteration is the same even if we set mini batch. but the mini-batch will start from the second iteration. This is because we have seen that in this way we have a good quality performance. You can see that from the second iteration on, there is a good reduction in. Oh no, sorry, I write 500. Okay. So from the second iteration, we can see a good reduction in time consumption at each step of the optimization. We can see here is 6 seconds for the dispersion optimization, and now it drops to 0.6 seconds. The performance are quite similar in terms of likelihood, but the time is really less. And if you want to use the generalized dispersion optimization, it will have one parameter for each genes of each gene. And in this case, I suggest you not to use the mini-batch on dispersion parameters. This is because it will slower the computation. So in this case, I set the common dispersion equal to false, that the default is common dispersion equal true. And now I will set n gene par equal to 50 and the same for n cell par. In this case, we do not have the improvement in time consumption due to the number of cores, but in the real case situation, you will have this. Okay. This is in this case is the same. The improvement in time consumption is shown starting from the second iteration, as you can see, and the performance are slightly better of the previous model, and this is because now we have a generalized dispersion, so we have more parameters. The NewWave will store the output of NewWave is a single cell experiment exactly like the input, but in the reduced dim slot there will be the latent representation that we have estimated. We can see in this chunk I will use t-SNE to represent our latent representation. As you can see, is a lot better than the one we have seen in the PCA. And if we do a cluster analysis on this latent representation, we have just a round index of 1. With the PCA, it was an adjusted round index of 0.10. So it's a good improvement.
Federico, there is a question. What kind of bias on estimation can we expect when common dispersion equal to true?
When common dispersion equal to true, so the default way, there is a slightly worse quality performance because we have the same estimation the same dispersion parameters for all genes. We still have a good performance, but obviously, if you want with the common dispersion equal to false is better because you have more parameters that describe your data. I don't know if it's enough. Okay, and as we can see, as we have seen before, there are more parameters, more than wu, the latent representation. Those parameters can be obtained using newfit instead of NewWave. So newfit has exactly the same parameters of NewWave. So X, verbose, children, and gene par, and cell par. but the output is different. It's not a single cell object, but is a new model object that has stored inside all the parameters that we have seen in the description of the model. It has exactly the same behavior. I have commented the view par only because for Docker, because it has problem with Docker. So here we can view par. You can see the X matrix that has always intercept, and in this case I have also the column of the batch. The V matrix that I have only the intercept, and V, beta, gamma, alpha, and zeta. Zeta is the dispersion parameters. So with this object, you can go further in the analysis of your model. And also with with a new model object, you can compute the AIC or the BIC of your data. Okay.
Yeah, this is what I mentioned earlier for choosing K. For example, you could run different values of K and then use this new AIC or new BIC function to kind of compare your models. And the lower, the better.
One of the most important works for this package is the framework for the layered array and HDF5 files. I will show it with 10x brain data. I will not really show because it's a huge data set, and so I will show how to use it and the performance, but I will not run the command. If you know, if you already know, 10x brain data is a data set, a layered array with stored inside 1.3 million of cells and 27,000 genes. You can load it in your workspace without problem because it is not really in your memory, but is the HDF5 and the layered array will read the data from your disk without really have it in your workspace.
Federico, sorry, you have to go to the console and type yes, otherwise it will not.
Thank you.
Yeah.
Okay. This will be long, so but it's not important for us because 10x I cannot make you see what is 10x, but it's a single cell experiment, and the only difference between the previous single cell experiment is that the counts is not a matrix but is a delayed array. Again, with 1.3 million of cell and 27,000 genes. There are some strength and some weakness of this implementation of NewWave. The biggest strength is that the huge reduction in RAM consumption due to the fact that we do not read all the data, but we read only a little chunk of this data that is always different. And the problem is that especially with iterative estimation like in NewWave, this continuing reading of the file can be slow. So, okay, 10x, we can see that is a single cell experiment, as we've seen, as I said, and the RAM weight of this object is really low, is only 304 megabytes, and the counts 10x is a delayed array. So the difference within when you use NewWave with the layered array, you don't have to worry about that. You don't have to set some different parameters. The command is exactly the same. It will read that is the layered array. The difference is a small approximation in initialization and the fact that the estimation of the dispersion parameters is forced to be generalized. You cannot change that. I will not run this because it is very long, and NewWave with the layered array is highly not suggested with small data. If you have to use a NewWave with small data, it's better to use the matrix implementation, and if you have big data, it's better to use the layered array framework. With this data set, we had these results in terms of time consumption. This comparison between I cannot show, maybe no, okay. A comparison between three
maybe you can try to make it smaller somehow.
Yes, okay. Can you see?
Yeah.
Okay. There are three different implementations. The NewWave with the matrix stored in the single cell experiment, and NewWave with an HDF5 and the layered array.
Well, maybe if you scroll up a little bit, we will see it better.
I cannot.
Yeah, this is good.
Okay. And this is from 10,000 cell to 1.3 million of cell, and always with 1,000 genes. As you can see, the HDF file, the layered array framework is slower, but not so slower. Is 8 hours against 12 hours. But due to the fact, due to the large reduction in memory consumption, we can use 40 cores, and now the time consumption of NewWave with HDF file is slower than the matrix implementation. And this is the I reduced the dimension. This is the sorry.
Yeah, you have to go back, I think.
And those are the result in terms of RAM consumption of NewWave with the same three implementation we have seen for the time consumption. As you can see, the benefit in terms of RAM consumption is very high.
Again, Federico, I think you need to scroll down a little bit.
More than this? I cannot do more than this without...
Yeah. This is time again.
What?
Can you scroll down from the... So we can only see your main window. We cannot see when you zoom in.
Okay. Okay.
So yeah, this is good.
Okay. We can see that we start from 10,000 cells to 1.3 million of cells, always with 1,000 genes. The consumption of the RAM consumption of the matrix implementation with 1.3 million of cell is like 420 gigabyte, while the HDF5 implementation is 60 gigabyte, and with 40 cores we have a duplication of the RAM consumption. That is a good thing related to the reduction in time consumption. So using, in this case, with 10x brain data, we are not doing batch factor remotion because we don't have batch in this dataset. We are only doing the reduction in the dimensional reduction. So these are the performance with this huge dataset. And thank you for the attention. The workshops is ended.
Okay, so we have, I mean, let's take the more technical question first and then the general question later. So the question that we have is from Chong Tang that says, have you estimated the CPU usage during this loading process?
The loading of the single chunk?
I'm not sure.
Okay.
If you want to raise your hand, maybe you can join us on stage to ask the question with more details. Or I also don't understand what you mean by loading process. Comparing to the memory consumption.
No, I didn't understand. The CPU consumption. Have you?
Yeah, well, maybe you can match offline in the conference after the workshop, because I also don't really understand the question. So we have a general question from Cristina Cheroni. Which are the advantages in applying NewWave rather than integration methods such as Harmony? I think I can take that question. I think this is a good question. Not only Harmony, there's plenty of integration methods, and also there are plenty of dimensionality reduction methods. I guess in general, each has their own strengths and weaknesses. I think one good feature of these, NewWave, but similarly to GLM-PCA and these other factor analysis-based models, is their interpretation. I mean, they're essentially linear models or generalized linear models. So the interpretation of the factors and the loadings is much easier than in other methods. Of course, that means also that we have to treat batches as a linear variable. So these other integration methods sometimes are more flexible. I hope I answered the question. And then we have a question by Kuhn Vandenberger. Here, you're working using only the highly variable genes. Would you recommend it in general? Are the factor loadings too dense when using all genes? I wonder how this would compare to using sparsity inducing estimation or initialization.
Okay.
As done in the keynote.
Yes, I will recommend the choosing the highly variable genes is the way I prefer when I analyze this type of data. And if the problem with using all genes is that I have seen that most of the times we have a really heavy computation. We have an increasing of time computation, but we don't have really an increasing of performance. So it's worthless to use all genes if it's not useless. And yes, I never try to using a sparsity induction initialization. That could be a good point for the future.
Yeah, I agree. I think you need some kind of gene selection, either with, in this case, it's a very simple, gene-wise variants, but there are other, deviance-based methods or like, coefficient of variation methods to select the genes. But I agree that having a filter on genes is usually good, not only for performance, like for computational performance, but also for the signal. It's more clear, or not definitely not improved when you use all the genes. Any other questions?
Yeah. From Christoph, what is the difference between Zimbi Wave and NewWave? Because he missed the beginning of the workshop.
Yes, the main difference is that NewWave assumes a negative binomial instead of a zero-inflated negative binomial. And even more, there is the way we parallelize the process, because ZimWave use BIOC parallel, while we use a PSOC cluster with the shared object error package that, as I said in the beginning, is allow us to share some metrics between cores, and that's avoid the memory, the increase in memory consumption. One of the main problem of ZimWave was the increase of memory consumption when you parallelize the process. Now in this implementation, we don't have this problem.
Any more questions? Comments?
Raise hand. I see a raise hand.
Yeah. Can you?
Yeah.
Yeah. Hi, Christoph.
Hey, yeah, hello. I have another question, but I think it's more easy if I do it live.
Yeah.
I was wondering, I really like this model, this known and unknown extraction of variation, factors. I was wondering, do you think there'll ever be, it will be possible to make inference on, let's say, the known factors? For instance, okay, we can adapt for batch, but for instance, we could also include another factor, or having an idea, are the differences significant or not? Or?
Yes, you can use whatever variable you want instead of batch effect. You can simply have to change the the formulation when run a NewWave. In this case, we have a batch in the call data of the single cell experiment. But if you put other variables, you can add other variables to these parameters. In X, you have the cell-related parameters, and in V, you have the genes-related parameters.
Okay. Yeah. Cool.
Yeah. So regarding inference. It's a good question. I mean, it's something that we've been thinking for a long time, actually, since Zimbi Wave, and I think Kun knows a little bit about the, he's, I guess in principle you could, do kind of like wall type tests on the betas, but we never really sat down and tried to write down the I guess I think it's doable. I don't know if it's convenient to do.
Okay.
You could imagine doing kind of a two-step approach instead, like similar to what RUV does, where you first estimate the factors and then you plug them in as known variables, and you run like a HRD-seq2 to do the inference.
But it would be cool to have this
No, definitely, and I think it's doable. I think it's just a matter of technically it might be difficult, but I think it's doable.
Okay.
So it's just a matter of finding somebody interested in doing it.
Okay. And with the right skills.
If you're offering yourself, that would be great.
I would be interested in doing that, but I don't know if I have the skills.
Well, I'm pretty sure I think people tend to underestimate themselves. So.
Okay, we'll see. But yeah, thank you for the answer.
Thank you.
Okay, I saw Laurent raising a hand. Oh yeah.
I think, Chiara, you're the only one that
Yeah.
yeah.
Maybe a silly question, but so NewWave is implemented for negative binomial distribution. What if I have data that is not negatively binomial, that does not have that distribution, kind of normal data, to keep things simple, but I would like to apply something similar?
No, that's a good point. So first of all, we should mention, I guess, the GLM-PCA method and package, which, in principle would work in your case because it's for, exponential families. But probably if you have normal data, you want some, like, you can go a step further and do something even more efficient than GLM-PCA. I vaguely remember there was an R package doing like supervised PCA or something. I don't remember exactly how they called it, but I can look it up for you, where basically they implemented a similar idea but in a simpler setting where you actually have, you can assume Gaussian data, you have PCA, but corrected for covariates. I will try to find it and link it somewhere. But yeah, the other thing that I wanted to mention is the GLM-PCA package, where you can choose any distribution belonging to the exponential family, and it's implemented in the GLM-PCA CRAN package, or in the SCRY bioconductor package, where they have nice wrappers for summarized experiment and single cell experiment. And so that you can specify like a binomial, a Poisson distribution, and the underlying model is very similar to this one. And I should say it's a fantastic work by Will Towns, and Kelly Street contributed or I guess implemented the SCRY package, and Will Towns developed the GLM-PCA method. So it's not something I can take credit for.
Thank you.
But yeah, and I will look for that supervised PCA stuff.
Okay, we have another hand, Edin.
Oh, right, Edin. Sorry, I should also have mentioned the Corral package, which is also implementing very similar ideas.
Yeah, I just wanted to mention we did this couple of supervised PCA methods. We implemented one called between group analysis, which is probably faster and cheaper computationally than a lot of ways. There's another one called supervised PCA that Daniela Whitten did, and GLM-PCA, they implemented two versions, the Poisson version and the negative binomial version. They recommend the Poisson version, which is of the Pearson residuals. That is identical to correspondence analysis, which can be done a lot faster. And actually, the way they recommend at the bottom of the package is to do it as you would correspondence analysis. So,
right. So just to sort of add on that, yes. So the GLM-PCA that I was referring to in the GLM-PCA package by Will is actually the full GLM-PCA model, which is similar to what we're doing here. So, working on the factor analysis model on the count. They also implement this what they call the approximation, which is the Pearson residuals, and the PCA on the residuals, which is the correspondence analysis, which is also implemented, I guess, more efficiently in the Corral package, right?
That's what we implemented. So in GLM, and I posted a link on like literally a side-by-side comparison of GLM PCA using their Poisson method and Corral. And one of the issues that you have with their method is because it's a random seed each time, you'll get a different approximation every time you do it. But if you repeat it, I can't remember what I did in that. I've done it a couple of times. If you repeat it 1,000 times and get like the most consistent method, it's the exact same as correspondence analysis. and correspondence analysis is as quick as a classic PCA. It's actually really, really fast because it's just a different transformation of the data before SVD. So if that is one of the things you want to do, it's just faster to do it in the Corral. It doesn't have all of the fancier bells and whistles of the full model, but if what you want to do is a simple GLM PCA, the Corral package will do it much faster.
And I think it's also implemented for sparse matrices. Is that right? Yeah.
So what we did is it's generalized at the moment. So we've implemented that you can call nearly any PCA method from it. But what we've implemented in it is Herbla. I think we've done random SVD and then standard SVD, but we can easily pop in any other SVD method, singular value decomposition method, that anybody else can do. So we can quickly adapt that.
I think we should write a vignette or something as a, to kind of have a summary of all these methods available in the bioconductor packages, so that people could, have an idea. Okay, if you need these are the options and the different packages that implement.
That's a good, because a lot of the times people have like either smaller data sets or bigger data sets, and maybe you just want a quick and dirty, what does this data look like? Yeah. Or sometimes you want something that's a much more complex model. And those are kind of two different use cases. And there's different packages that are better for one case or the other. Sure. So yeah, that seems to be a sensible kind of thing to do. Yeah. Anyway, I posted the link. On the workshop that we did for the bioconductor meeting, I think we took 10 different packages that do PCA or variants of PCA. And we compared them all, and we show like what's the difference between a singular value decomposition and a pre-comp and a PRIN comp and all the rest of these and how they're all equivalent. But we could equally do that for any of the other bioconductor packages. PCA Tools is another really good package, which has a lot of nice methods and implementations in it as well. But yeah.
Thanks, Adi.
Probably a good thing to do. Anyway, I just
having I imagine it like a big table where you could see the packages and does it support sparse matrices? Does it support HDF5 and all the features that they have?
That's really good, and I probably Casper would be another person who knows. There's a couple of, we could get like a whole collection of us that are into this, and hopefully
it seems very in brand with what we should do with the CZI group, right?
Okay, I'll let somebody else talk.
Okay. Thank you.
Any other raised hands?
No.
Okay.
No question, no raised hands, no fit. Okay. So, thank you to all. And
I think it's time to have dinner, right?
Yeah. See you tomorrow in the afternoon. Okay.
All right.
Thank you.
Thank you. Bye-bye. Bye-bye.